How does microscopic shear make metals break? Have you ever wondered why metals can suddenly break without warning? The answer lies in microscopic shear. This phenomenon plays a key role in how metals fail under stress. When a metal experiences shear stress, it means that forces are acting on it, causing its layers or particles to slide past one another. This sliding creates localized deformation along specific planes within the metal. As this deformation occurs, it concentrates strain energy in certain areas. This leads to the formation of microscopic shear bands or zones where the material begins to yield and weaken. At this small scale, shear failure starts with tiny defects like microvoids or dislocations. These defects grow and connect under continued shear stress, forming narrow regions known as shear bands. Within these shear bands, the atomic structure of the metal becomes highly distorted. This distortion reduces the metal's ability to carry loads effectively. As these shear bands develop and merge, they create cracks that can spread quickly, ultimately causing the metal to fracture. Interestingly, the arrangement of atomic scale disturbances plays a role in this process. For example, certain patterns can organize plastic flow into shear bands that are oriented at about 45 degrees to the applied compressive stress. These shear bands representing the lowest energy state under high strain and serve as precursors to larger failures. The conditions of the material also affect how microscopic shear leads to failure. Factors like temperature, strain rate, and environmental influences such as corrosion can speed up crack initiation and growth. In high-temperature scenarios, for instance, creep deformation can make it easier for voids to grow and merge. Understanding microscopic shear is essential for explaining why metals can fail suddenly, often without visible signs of prior deformation. When examining fracture surfaces under a microscope, you can see features like striations and crack branching that trace back to shear failure mechanisms. This knowledge is particularly important in industries such as automotive and aerospace. In these fields, preventing mechanical breakdowns involves managing shear stresses and monitoring microscopic damage to avoid serious failures. In summary, microscopic shear causes metals to break by concentrating deformation into narrow bands where atomic bonds weaken, leading to crack formation and rapid fracture. This explains many mechanical failure modes where shear stress is the main cause, linking small structural changes to the larger breakdown of metal components.